see if that looks like it's doing well so far. Okay, so this is going to give me some new roots that we will pile on to the roots that we already had earlier. So what are the new roots that this annihilator gives us?
-1 and 2.
-1 and 2. Right. So then the particular solution, excuse me, the particular solution here would look like what? Ax cubed e to the negative x plus b e to the 2x, right? Okay. That right there is what I call the form of the particular solution. And if I ask a question and I say find the form of the particular solution, then that's all I want you to do. Please don't go any further than that. I might ask you to actually find the constants. Probably won't ask you to do that a lot on a lot of problems, but I might ask you to do it once on a problem. And again, you have to trust me that I'm going to give you something reasonable. This one is kind of borderline unreasonable. The reason I say that is, well, first of all, you look how many derivatives you're going to need. You're going to need 3 derivatives of this. The second term isn't too bad, right? But the first term, product rule 3 times, that's going to mushroom out into a lot of terms. Yeah.
You know, you have ax cubed e to the negative x. Who's to say that that can't be like a e to the negative x, and that one's like that's the a and that's c1. You know?
Oh,
you know what I'm saying?
well, the lower terms with where there's no x's, 1x and 2x, those have to go with the complementary function.
They just have to.
Yeah, the complementary function terms come first, and then the non-homogeneous part.
It just has to be that way.
It has to be that way, yeah. I mean, and technically it wouldn't be wrong if you called this C4 and C5, but I just think it's confusing. People start getting this part of the problem confused with this part of the problem, so I like to use some different letters here. Okay. So anyway, it wouldn't be very hard to find B in this case, because taking derivatives of this and looking at the B part is with the e to the 2x, and you'll be able to match that up on the right hand. Remember, you match up the left side and the right side. So the B part could be matched up with the 3 right here. This doesn't mean B equals 3, by the way. You still have to plug this in. You have to plug this thing into this left-hand side and see what happens. So for example, 3 derivatives of b e to the 2x is going to give you 8b, right? And then plus 3 times 2 derivatives of b e to the 2x would be 4b. And then 3 times 1 derivative would be 2b. And then the original, which is just b, and all of that would have to equal 3. And I'm just not writing down the e to the 2x part. Yeah,
so
Sergio?
when we're trying to find the constants, we
Yeah.
have to do them one by one. Like we don't do the derivatives of that all together.
No, you do. You do. I'm only not doing that here because it's going to be a nightmare to do it.
Oh, okay.
Yeah. Please, if this is confusing you, then don't listen to me right now. I'm just trying to show you that getting the b part is easy, right? Because basically you're going to get what 27b. 27b is equal to 3. So b is 1/9. That one I can get pretty easily. It'd be very hard for me to ask you to find one of the constants. I suppose I could. I could say, write down the solution in the form of, and I could give you the notation for because otherwise it wouldn't be wrong. I couldn't just say find B, because somebody might do this. Right? Then that's not wrong either. That's still the correct form. It's just writing them in the opposite order. So I'd have to find a clever way to ask the question so that without giving away the answer to what the form is, I'd ask you for the second part. I don't know. We'll see if I figure that out. Okay, so can I skip finding A and B here?
Yeah.
Okay, I think we'll probably do one later on where we actually go all the way through it. Yeah.
For that, so we get x cubed e to the negative x,
Yeah.
which matches the right side on the original equation.
Yes, correct.
Is that always the case for the new roots?
Yeah, you're always gonna take this whole thing and match it up to this whole thing.
I know, but are our roots always gonna give us like similar to the
Similar
roots of the
looking
right side?
terms?
Yeah.
Yeah, they absolutely will.
Okay.
It's because of the nature of the annihilators, right? The annihilator of e to the 2x is what? It's d minus 2. What root did that give me? It gave me the root 2. What did that give me? It gave me this term. So see, this term came from this term.
So if we don't get like the roots, if they don't give us nothing similar to that, we probably did something wrong, right? Okay.
That's true. Okay.
That's right. One quick question.
Yeah.
So I've noticed this before, like on the when we're doing annihilators, or at least this type of annihilator where it's like with the e to the x.
Yeah.
The yp equation, the exponents are always the same. Is that always true?
That's what he's just asking me.
Oh, okay.
Yeah.
Sorry.
No, that's
So
okay.
you can kind of quickly check your answer real fast.
Yeah,
by
you
comparing that.
kind of know that because if you think about what does it take to annihilate these guys, well, exactly the thing that gives you these roots is exactly what gives you those terms that look like what you had before.
Beautiful.
Yeah. But you have to do this part after you've done the complementary piece, so that you know how many repeats you've had, so that you know, for example, that this is x cubed. Does everybody understand? If you stop at x squared right here, then when you come over to the particular part, you pick up where you left off. So if you left off with x squared, now you're starting here with x cubed. Okay, great.
The general form just add.
Yes, right, the final answer, exactly, would be just simply y sub c plus y sub v. I'm okay with you just writing that down as long as you have shown me clearly these two parts. If your work is so confusing I can't figure it out, then it's hard for me to make heads or tails of it. Okay? So try to be neat if possible. Okay. Everybody hanging in there?
Yeah.
Kevin.
In the original problem, did it ask for just the form of YP, or did it say just find a general solution?
This one just said go back and solve as many as you have time for. This was a group work problem.
Gotcha.
I believe in the solutions I didn't even do it, because which means it must have been pretty bad. Oh, here it is. Yeah, I just said substituting into the differential equation and equating the coefficients on the left and right sides, we can solve for A and B. So I didn't actually do it. So that gives you a litmus test of like where I draw the line is something that's too hard to actually do. Okay, everybody hanging in there so far? Okay, let's, that's all I'm going to do off of that group work. Let's go to the actual review session questions now. Okay. Yeah, let's do this. Let's start with this one. I'm going to start with the very first one on the sheet. People really struggle with these conceptual things, so let me give you one. So suppose that a cubed minus 2a squared plus 4a plus 5i is equal to 0. And then suppose lambda is an eigenvalue of a. And then show lambda cubed minus 2 lambda squared plus 4 lambda plus 5 is equal to 0. Okay. By the way, this sort of thing is true for any polynomial expression like that. There's nothing special about this particular one. Those numbers are just completely random. So what is the point? The point is that if you have some relationship among the powers of a matrix. That same relationship has to hold for the eigenvalues too. Okay? So that's what we're going to show right here, is that that's true. Okay? Does anybody have an idea how we would start?
You could start with the fundamental thing we know that a x vector equals lambda x vector.
I'm going to use V,
Okay.
but I like
Good
the idea. I mean, I don't know how many people this happened to on the quiz, but if you just wrote that down on that theoretical problem at the end of the quiz, I gave you 1 out of 3 points just for writing that down. Without even turning on your brain, you just know that equation. I gave points for that because that is an important equation, right? So AV equals lambda V. I do want to point out here that an eigenvector V has to be not 0. So we have something like that. Did I say anything about the matrix being invertible? No. So I don't want to see an A inverse anywhere. I don't want anybody dividing by a matrix. I don't want anybody dividing by a vector either. I see people do this all the time. I'm going to divide by V. And I'm like, oh.
You never even showed us that.
No, you've never seen me divide by a vector this entire semester, so I don't know where people get these ideas from. But they do. Or the other one is, of course, you cancel the vector. You cancel the vector and you write this down. And I usually have to go, you know, I have to go have a counseling session after that too, because now you're saying that a matrix is equal to a number, and this is not good. So please don't do things like that. That you cannot do. Now what we want to do is kind of show this equation, right? And we have these higher powers here of A, right? So we have this boxed equation, and we have this right here. Does anybody see?
Can they multiply by lambda in the top equation and then?
Multiply by lambda up here? You can, because it's a scalar. Then you'll have a lambda times an A. So you'll take the lambda is multiplied by the A. But you see down here, the lambda is on the other side of the equation from the A. So it wouldn't lend itself so well to using this equation, in my opinion.
Can you set the A equation with the lambda equation equal to each other?
Set this equal to this?
To the lambda equation. Lambda
Well,
cubed.
this is what we're trying to show.
Oh.
This is another thing. We don't know it yet.
Oh,
If we don't know something, we can't use it. That's a famous fallacy of writing proofs. So we don't actually know this one yet. We know this and we know this. This one involves higher powers of A. This one just involves A.
oh, yeah.
Yeah.
I don't really know, but I feel like a squared times a vector v is like near what we want.
Let's just look at this. Exactly. What is A squared times V? This just means A times V. Right? And then you see your AV right there, which you can change to lambda V. So this becomes A lambda V. Well, we have to be so careful. This is a matrix, this is a number, and this is a vector. 3 different objects in the same span of that right-hand side. Yeah.
So because the lambda is a number we can pull at x, it's just a scalar.
That's
and then
exactly right. We're going to pull the lambda out in front, and then we have the A next to the V again, don't we?
Yeah.
So then we get another lambda, and do you see that you get lambda squared V? Let me write down one more step here. We already have one of the lambdas. Now we're going to get another lambda. That's just 2 lambdas times V. Lambda squared times V.
Oh, because AV equals lambda V, right?
Right. I used this twice, actually. I used it right here, and I used it again right here. I used it twice. Okay, that's a big key. So see what's really going on is you're kind of converting the matrix power to the eigenvalue power, which is exactly what you really are trying to do up here. You're trying to take this equation involving powers of A and turn it into the same equation involving powers of lambda. So, so what else might we be interested in calculating here?
A to the third, the same way we did a squared.
Right, right. So I'm just going to say, let you guys check it. Similarly, a cubed v is equal to lambda cubed v. Okay? Is it making sense?
Yeah.
For a second? Yeah, one.
You know how in the matrix equation, the
Yeah.
A equation, it's negative 2a squared?
Right.
You don't write that down when you're proving it?
We're gonna need that. I'm just not that far yet. Right now, I'm still not done with the solution. I'm trying to run the review instead of just sort of saying, here's the answer.
Yeah.
I'm trying to sort of get it out of you guys because it's better for you guys to kind of take it slow and work it through. So for right now, we've kind of looked at a cubed, a squared, a, right? Those are the pieces of that equation on the top. And we've realized that basically the powers of A just turn into the powers of lambda. So I've done all that work. Let's see, for example, 2a squared v is just going to, this 2 here is just going to go along for the ride.
Okay.
The calculation is going to be completely the same. Dot, 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 2 lambda squared v. The 2 doesn't even do anything. It just kind of sits there. Right? So what I hope you guys are realizing is that if we take a cubed minus 2a squared plus 4a plus 5i and we apply it to v, the whole thing to v, then what do we actually have? We have a cubed of v, which is lambda cubed of v, excuse me, minus 2 lambda squared of v plus 4 lambda, and then identity matrix is just like it's not even there, so it's just 5v. And does everybody buy that? And this thing right here, this matrix, was the zero matrix. So if this whole thing, what do you get when you take a zero matrix and multiply it by a vector? The zero vector, right? So if a matrix of all zeros and you put a column vector next to it, it's just going to make that column vector 0. So this actually is equal to 0. Since a cubed minus 2a squared plus 5a, I'm sorry, plus 4a plus 5i is equal to 0. So what do we have? We have some number times our non-zero vector v becoming 0, or equaling 0. So if I take a non-zero vector and I multiply it by a scalar and get 0, what does that scalar have to have been? This has to be 0. This has to be 0, okay? Because if this was not 0, guys, if this was not 0 and v is not 0, then you're just going to take the non-zero vector and stretch it. It's not going to be 0 yet, right? So this scalar must equal 0. That's the reason. Go ahead.
Before you get to that part, would we have to check each individual piece first before we actually write down what you just wrote down?
You could actually do it in one big fell swoop. I just didn't want to present it that way again because that's too polished. That's the way I would prove it, having done this for many years. But for somebody who's doing it for the first time, it's kind of better to take baby steps. AV equals lambda v, so then look at a squared v and a cubed v. You can just kind of take it one at a time. And my goal is always with these things is to have you convinced, I don't know if I'm doing good job of it or not, but have you convinced that you could do this? Right? Maybe you couldn't do it before, but now you see it like, yeah, that makes sense. I could do that if I saw it again. Yeah. Go on.
So like, for the 1 or 2 questions that you're gonna give us of this in the test, it's always gonna be true, right? Like, it's not gonna be, is this true or is this false?
I may give you true false items, but I will tell you if it's true or false, right? So, for example, every invertible matrix is diagonalizable. That's false. That's in one of those group works. You go back to group work 11, I believe.
Yeah.
Every invertible matrix is diagonalizable. That's false. If something's false, I'll be looking for an example. I'll be wanting you to give me an example. In that example, you would use a 2 by 2 matrix that is invertible,
No,
but
but
is
I mean,
not diagonalizable.
like the conceptual stuff like this. It's
Well, I
always gonna
consider
be-
that question to be conceptual too.
Okay.
But yeah, anything like this, if I say show something,
That
if I ask you to
means-
show something, it means it's true.
Okay.
It means show it, because it's true. I wouldn't ask you to show something that's not true. That would be, well,
That would be mean.
that would be a reason for me to like lose my job or something. So yeah, I wouldn't do that. We?
So in this question, you can distribute the vector v to all the matrices. So
Yeah.
you can make that jump there. Then from there, you can factor out that v and have the scalars by themselves.
That's very true, yeah. Either way you want to do it. You can either have the v factored out right away at the very beginning and then distribute the terms, or you can do each term individually first and then bust the v out to the end. Guys, try to do things well in the sense of how you write stuff up. You know, sometimes people get a little sloppy. I'll see stuff like this, the vector in front of the matrix. That really bothers me because I harp many, many times about how important it is that matrices don't commute, and so you shouldn't be writing something like this down. If I gave you that vector and asked you to multiply it by this matrix, right, you should be asking me like, you know, what side of the bed did you get up on? Because this doesn't make any sense. I can't take a 3 by 1 and multiply it by 3 by 3. So please don't be sloppy with this stuff. Just write things in the proper order. Vectors should be to the right of scalars and to the right of matrices. Yeah, go ahead.
So in this particular problem, the reason we knew v was not equal to 0, the vector v, is because in a v equals lambda v, v is never equal to 0.
Right, V is an eigenvector,
Right, which is never 0.
which is never 0. Okay. Let's see, do I want to do that one? I think I'm going to skip that second one for now. Oh, I already did that. Some of these some of these that were on the group work are actually on the review question, so that's good.
Number 5 and number 6.
Yeah, I noticed that. Okay, I'm going to jump around a little bit to try to cover a lot of different stuff. So I'm going to go actually to the very last problem on the review sheet. Okay, so this is actually number 8 on the review session questions. It says, find 3 linearly independent solutions. And it says, check linear independence. 2, here's the differential equation. X cubed y triple prime plus x squared y double prime minus 2xy prime plus 2y equals 0. We're going to assume x is positive. Of the form y of x equal x to the r. Okay? So, the thing about this question is that this type of differential equation is not one that we study. I mean, it is a third order linear differential equation, but its coefficients are not constants. We don't have an auxiliary equation for this, right? If we had an auxiliary equation, we would write it down, we would find its roots, and that would tell us how to piece together the complementary function. By the way, this is homogeneous, so we don't have to do any particular solution here. But in terms of the equation on the left side, that's not something we've studied. It actually is in the book, it's just in a section we didn't cover. But I can still ask this question because we still have the theory that we learned. So the theory that we learned is that any third order linear differential equation has a three-dimensional solution space. So if you can find three linearly independent solutions, all other solutions are just linear combinations of those. And the reason I can still ask you this question, even though we never covered it, is because I told you what form for the solutions that. Like normally we use e to the rx, right? That's our usual, that's the one we use whenever we have a constant coefficient differential equation. We use e to the rx and then we get our auxiliary equation and go from there. We're not going to use e to the rx here. Why not? Because it's not going to work. This type of differential equation, e to the rx doesn't work for it. Turns out what you have to do to make it work is use this one. So, but you're not supposed to know that because we didn't cover it, so I obviously wouldn't expect you to just know that x to the r is the right form. I have to give that to you. And you're going to see a problem on the sample test from when I gave this exam last year, where I did the same thing. I basically gave people a differential equation that we had not looked at. So I didn't expect people to know the nuts and bolts details, but I still expected them to know sort of the broad approach, which is to find linearly independent solutions and then build the general solution out of them. So let's see if we can do this. If we're looking for solutions of the form x to the r, what am I going to want to do to solve that?
Three derivatives.
Right, I need to take derivatives. I need actually three derivatives, that's right. Three derivatives of that x to the r, right? Okay, so let's do it. So this is the boring part. Oops, y prime. This is the boring part. We just have to use the power rule. So we get r times x to the r minus 1. Hope everybody remembers their derivatives. Then we have y double prime, which is r times r minus 1 times x to the r minus 2. And then y triple prime is r minus 1 minus 2 x to the r minus 3. Believe it or not, we actually did this in the first week of the semester.
Yeah, I remember.
Way back to the very beginning. The only thing is, at that point, we had no idea what linear independence was, right, or how to build a general solution to anything. We just, I think back in chapter 1, all we said was, find the values of r that work.
It was on the quiz on the first quiz.
The very first quiz, yeah. So yeah, it goes back. It's all coming back around. Okay, so now we have to put everything in. So let's plug it in. So what do we have? We have x cubed times three derivatives. So that's going to be r minus 1, r minus 2, x to r minus 3, plus x squared times the second derivative. I'm just going to write it down here. Minus 2x r x to the r minus 1 plus 2r x to the r minus 1. No. Plus 2x to the r. All of that equals 0.